So I'm sure everyone knows what infinity is. If you clicked on this video, surely you're at least familiar with the concept of infinity. But did you know that sometimes infinity can be greater than itself? Well, that's a little bit misleading because it's not necessarily like you think of it as a number. One can't be greater than one. Any number can't be greater than itself. But that's the thing. Infinity is not a number, it's the amount of numbers there are. And that's a really important thing to think about. Keep that in mind throughout this video, it might be helpful. The overall idea here is the difference between countable and uncountable infinities. But again, what exactly does that mean? Well, firstly, that's what we're going to be breaking down. I'm basically going to show you two sort of methods of comparing these two terms to explain, one, of course, what the difference is, but also just hopefully help you gain an appreciation for how infinity works, I suppose. If we take a look at a countable set first, we have 0, 1, 2, 3, blah blah blah. And it's important to think of countable not as necessarily countable, but you can start counting it. So if we go all the way up to infinity, we count all the numbers, all the whole numbers that there are. Well, you can't count all of that. There are literally infinite of them. There are like even if you went forever, for all of time that will ever exist, there'll always be a higher number, another one to go to. But you can start counting. Well, you're like, what's something that you can't start counting? Well, what's the first real number after 0? Not 0.1, not 0.01, even smaller. Even smaller. There's, like, even if you go as small as possible, that it's infinitely close to 0. So 0.000, there is an infinite amount of zeros, and then a 1. Well, you can always make it smaller again just by halving it. Change this 1 to another 0 and a 5, and it's already smaller. Or if you change it to another 0 again, and then a 1, another 0 and a 1, another 0 and a 1, just divide it by 10, etc. Keep going, regardless of what you come up with, and be like, this must be the smallest number. You can always make it smaller. Divide it by anything, divide it by infinity, and you can, regardless of how small you get it, you can still keep going. So, that's the thing. What makes it uncountable is the fact that you literally cannot start counting it. You can start at 0, but where do you go from there? Even if you went negative, what's the first number you go to next? That's what makes it uncountable. So hopefully that explains the difference between countable and uncountable. But now we're going to take a look at what actually makes the countable set smaller than the uncountable set. You'll be seeing some chapters along the bottom here of the screen. Basically, this first method, which includes this, is a very common way of analyzing this. It's probably what you already know if you've ever been taught about these two different words in the context of infinity. So if you have, you may want to skip to the second one. But this first one will be very helpful if you've never learned about this stuff. Before actually doing the proof that uncountable is larger than countable, we're going to actually look at a case where two sets are the same size. They're both infinite, but they're the same size. Now this may seem unintuitive once you see what the two sets I'm going to use are, but let's have two sets, A and B. A is going to be 1, 2, 3, 4, etc. forever, and B is going to be 2, 4, 6, etc. And already you can visually see that these numbers only occur like half as often. So if you went on forever and you left it like this with gaps in the middle, you'd be like, well, at any given point there are, like, say if you go up to 1,000,000, there will be half as many even numbers as there are total numbers. But that's the thing. That will be the case if you got up to any specific number, but when you go until infinity, there are the same amount. A good way to look at this and hopefully understand this comparison is by looking at it as if it was a material. So you can rephrase B by packing it down and taking out the gaps and looking at it as though 1 turns into 2 by doubling it, 2 turns into 4 by doubling it, 3 turns into 6 by doubling, 4 turns into 8 by doubling, so on and so forth. So by packing it down and making it denser, basically within one step here we've gone up by 1, but within one step of this set we've gone up by 2 integers. So therefore B is denser. Now if you think of it as a material, in any finite amount of space, say you have a really dense material and a really, I don't know what the opposite of dense is, but I guess a light material. That might not be the right word, but hopefully you know what I mean. A non-dense material. So if you have a cubic meter of the dense material, there will be more physical mass in it. It will be heavier because the material is denser. A cubic meter of the light material will be lighter, of course. If you dig 2 1 by 1 by 1 meter holes in the ground, you fill one up with bricks, one up with feathers. All those bricks and the feathers take up the same space as each other, but the bricks in there are much heavier than all the feathers because the material is denser. So it's the same concept here. For any finite amount of terms, so the first 20 terms of this, you only get up to 20. The first 20 terms of this, you reach 40. So for any finite number, you will get higher by counting the first 20 numbers in this set than you will by counting the first 20 numbers in this set. For any finite number, that is the case. But if you look at it as infinite, well, for any infinite number, you will reach infinity. For any infinite number here, you will also reach infinity. If you build an infinite amount of materials, say if you have an infinite amount of feathers, it will weigh infinity. An infinite amount of bricks still weighs infinity. On an infinite scale, they're equal. And think of it in the same way, in order to count up to infinity, you need to have infinite terms. You need to go on for an infinite amount of time. And same with B, in order to reach infinity, you need to keep counting for an infinite amount of time. This applies to materials as well. In order to fill up all of infinity space with feathers, you need infinite feathers. In order to fill up infinite space with bricks, you still need infinite bricks. So hopefully that explains it. Not to look at this set as actually having less, but to look at it as being packed in more, being denser. So this is an example where two sets, although this one is denser, the two sets are still the same size. Now, let's actually do the proof of why uncountable numbers are a larger set, because you'll notice with that set, with that example, we had A and B, blah, 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 and we basically mapped them onto each other. So for any given number A, we just doubled it to get the corresponding number B. So the fifth term of A is 5, and the fifth term in the set B is double that, 10. So they are related in that way. For any number B, there is a corresponding number A, and vice versa. Now, the entire fundamental idea here of why uncountable numbers do not match countable numbers is the fact that you can't assign numbers to each other like this. So in this case, if you went up to infinity with A, you would also go up to infinity with B. So once you fill up all the A numbers that there are, you will also have filled up all the B numbers that there are. So this may seem illogical because once you go to infinity, this number should be twice as much. Well, no, because it's infinity. Any number, say if you're aiming to reach 20, you will reach it in B first, but if you go on forever, any number you can think of will be in both. Well, of course, not odd numbers and not decimal numbers, but any number that is in B will also be in A eventually, just a little bit later. But we can't map numbers to each other like this when we do real numbers. So let's put this in a table. So we have this table. It only goes up to 5 for now, but pretend it goes on for infinity. And this will be all the integers. You'll notice there is an awkwardly large space here. You will see why in a minute, but for now just pretend it's because I'm really bad at drawing straight lines. So let's just start filling these up. Of course, as we have discussed, it is impossible to figure out what the first real number is because you can always go smaller. So that we will very quickly realize if we try and just fill up this table that you can't, there's nowhere to start. Well, I suppose we can start from 0. So let's do that. We will have just infinite zeros here. That's fine. But where to next? Well, there's nowhere to go. So for the next term, let's just generate something random. And then let's just continue that. Obviously, again, we only have 5 here, but it would go for infinity, and each term would have infinite precision. There would be infinite decimals going on here. So we've now filled out all of the decimals. Sorry, we've now assigned a decimal number to every single integer that there is. We've gone to infinity, we've gone to negative infinity. Obviously, we haven't actually, but let's just say we filled up all the numbers. If these sets were the same size, by the time we reach infinity on the left, we would have also reached infinity on the right, as we proved up here. But that's not the case. And I can prove that very easily because even though we filled up all the integers, there is still a repeatable way to create a brand new real number that isn't in the list at all. How do we do this? Well, let me grab a highlighter. Start by going down in a diagonal line, and so you highlight the first number of the first, you highlight the first digit of the first number, the second digit of the second number, and so on, going down in a diagonal line like this, forever to infinity, and then simply write out all these numbers, but add 1 to each one. So we have 1, the 7 turns into an 8, so we got 1.8, the 8 turns into a 9, 4 turns into a 5, the 9 will loop around and turn into a 0, and so on and so forth. And now we have a brand new number that, because of the way we created it, this number is by definition different to every single other real number in here in at least one spot. So therefore, it is a brand new number that doesn't have any mapping. There are no integers left to map it to. We've used every single integer, and yet we've just created a brand new real number. Let's say, for example, oh, I made a stupid mistake. I didn't do 0. Okay, fine. Let's say there is one number we missed. Whatever. Doesn't matter, because we can just do it again. Let me grab a different color. Highlight the first number of what is now the 0th term. The second number of the next one. Then the third one, fourth one, fifth one, so on and so forth. And then obviously we don't have, there's no more space at the top to write this out, so I'll just do it at the bottom. We have 1, which turns into a 2, 0, which turns into a 1, 6 turns into a 7, 2 turns into a 3, 3 turns into a 4, so on and so forth. And now we have this brand new number that yet again cannot be mapped to any integer because we've used all the integers, but there are still more numbers to be created here. So, if that makes sense, hopefully it has proved that the amount of real numbers, I just wrote an M. The amount of real numbers that there are is greater than the amount of integers that there are. And therefore, uncountable infinity is greater than countable infinity. Hopefully that proof makes sense. For any amount of numbers you can create, you can be like, oh, well, I missed a number here, whatever. No, you can keep going forever. This, even if you fill up all these, you can always create more real numbers, and that is the reason why this set is bigger. That is the end of the first proof. Now we're going to move on to the second one. Alright, so the second proof I literally came up with this morning while going for a walk, so it might be a little bit all over the place. I'm trying to sort of remember it as I go, basically. I have some notes pulled up here on my laptop, so I'm just going to kind of follow along, but there might be a few more jump cuts just because I'm trying to work things out. We're going to start with the same sort of plan. We have a set of countable numbers, and then we have a set of uncountable numbers. Actually, I'm not going to call it uncountable, I'm going to call it decimals. So let's start with a countable number of decimals. Let's start by saying we have one decimal point of precision. So starting from 0, obviously 0, the integer 0, the countable 0 will be assigned to the decimal 0, fair enough. Now, if we step up, if our precision is 0.1, that means that we're stepping up by 0.1 each time. So the countable 1 will be assigned to the decimal 0.1, 2 will be 0.2, and so on and so forth up to infinity. This is of course countable. Hopefully you can understand why. If we had a higher amount of precision, say our precision was 0.01, then we will just need to be, of course, a little bit more precise. We add an extra 0 in here. The countable 1 is decimal 0.01, countable 2 is decimal 0.02, so on and so forth. Again, this is still a countable set, but no matter how far you go with the precision, you will still have a countable set here. This decimal set will always be countable. However, here's the big idea. Real numbers have infinite precision. Now, of course, not all of them do. 0.25 is a real number, but it only needs 2 decimal places of precision to be represented with perfect accuracy. However, pi is also a real number, and it goes on literally forever. So, it is also a real number, but this is an example of one that does have infinite precision. Once you get to, like, the last digit that humans are aware of, there is a repeatable way to calculate what comes next. It requires quite a lot of computing power, and no human brain would ever be able to catch up with how much computers have discovered of pi, but there is a repeatable way to calculate it. So we have a number line between 0 and 1, and we have a precision of 0.1. Well, it's simple. We have 0.1, 0.2, blah blah blah, up to 0.9, as we know. When I said that the precision is infinity, what I should have said is that the precision is 1 divided by infinity. So if infinity is the number furthest away from 0, or not the number, it's the amount of numbers there are, but if we were to think of it like a number, it would be the furthest possible number away from 0. 1 divided by that is the closest possible number to 0. So when we have that level of precision, even between 0 and 1, there is no first step to make. We already know this, but this is the entire definition of what makes it uncountable. In this case, we have 1 decimal place of precision. If the precision is 0.01, then we have 2 decimal places. In this case, when it's 1 over infinity, we have infinity decimal places. When you have 1 decimal place, there are 10 numbers between 0 and 1. When you have 2 decimal places, there are 100 numbers between 0 and 1. So, to generalize this formula, when you have n decimal places, there are 10 to the power of n numbers between 0 and 1. So say we have 4 decimal places. That means we'll be able to come up with 10 to the power of 4 numbers between 0 and 1. With infinite decimal places, there will be 10 to the power of infinity numbers between 0 and 1, which is just an unimaginably large number. So, just to sort of keep track of the things we've decided on so far, the one important thing to keep track of is that from 0 to 1 there are 10 to the infinity numbers, assuming that we have infinite decimal places. Fair enough. But now, let's do something else. Now let's say we go from 0 to 10. Well, that means there are 10 times as many numbers within the range. So, if we have 1 decimal place, it's 10 times 10. There are 100 numbers between 0 and 10. With 2 decimal places, there are 1,000. With n decimal places, there will be 10 times 10 to the n. This is equal to 10 to the power of n plus 1. Hopefully that makes sense. With infinity, that's a really poorly drawn infinity, but with infinity decimal places, there will be 10 to the power of infinity plus 1 numbers. Now, hopefully you are aware that infinity plus 1 is the same as infinity, because, like, say, if you reach infinity, and then you add 1, and there's still another number, well, that doesn't mean that infinity, doesn't mean you can go past infinity. It just means that you were wrong about where infinity was, and you were below infinity. Also, I know you can go past infinity, but not with counting numbers, so we're just going to ignore that. Obviously, again, infinity isn't a number, so this is kind of a failed analogy here. But just keep in mind, infinity plus 1 is the same thing as infinity, because it's just the amount of numbers there are. If you add an extra 1, that just means there are more numbers in existence. And of course, there are infinite numbers. I'm just going to end up repeating myself here. To be honest, I'm not really sure how to explain why this is true. Hopefully, it's just like a logical fact. If it's not, I'll see if I can find any sources about it and link them in the description. That means that it's basically equal to 10 to the infinity. So, that means that if we bring this card back here, from 0 to 10, there are 10 to the infinity numbers. Now, that means that the set from 0 to 10 contains within itself a set of the exact same size. In the realm of integers, the only possible set that contains within itself a set of the same size is the entire infinite set. Within the realm of integers, there is only one set that contains within itself a set of the same size, and that is the entire integer set, which is infinitely long. However, as you can see, when we move on to real numbers, there is a set that is only from 0 to 10 that happens to contain within itself a set with the same amount of numbers in it. We are observing a property which is the ability to contain within itself a set of the same size. This property only exists for infinity when you're working with integers, but the number 10 has the same property when you're working with real numbers. But in fact, say we had another set that goes from 0 to 0.1. With one decimal place, there is only one step. 0, 0.1, you're finished. With two decimal places, there are of course 10 steps. With n decimal places, there are 10 to the power of n minus 1. Therefore, for infinity decimal places, we have 10 to the power of infinity take 1, which is still infinity. Now you can imagine repeating this process to go down forever and ever, getting smaller and smaller, and you can still always prove that there are 10 to the infinity numbers within that set. In fact, the process could be repeated an infinite number of times, and you could prove that the smallest possible number you can imagine still has 10 to the power of infinity numbers within it. So, the smallest possible number that we can represent is 1 divided by infinity. Like, it's literally 0 followed by an infinite amount of zeros and then a 1. Like, the smallest possible number. But, it's still not 0, so it is possible to say that there are 10 to the infinity numbers even within this tiny little number. So it can be repeated an infinite number of times to show that any range of real numbers is larger than the infinitely sized range of integers. So this number 1 over infinity, it's that small, that unimaginably small, and we can still break it into infinite pieces. Not even just infinite pieces, an uncountable number of pieces. So if you repeated this process infinite times and got a number that is just incredibly tiny, like so unimaginably small, hopefully you can believe that, where'd my paper go? Remember the thing we did where we had a table and we tried to assign integers to decimals and then you could create a new one by following the diagonal line? Yeah, if you tried to do that with these incredibly small numbers here, you could imagine, you would absolutely, there's no way you can, assign integers to them. It is just so incredibly small. So, the set of real numbers is so much larger than the set of integers that even the tiniest unimaginably small portion of it can still be broken down into infinite pieces. In fact, the set of real numbers is infinitely larger than the set of integers. Let me know what you think, if there is any way you think I can make this a bit more understandable, anything I can improve just in general in the future. But yeah, other than that, thank you for watching, and I guess I'll see you next time.